PhD is an engineering manager at Schlumberger, and I think it'll be immediately apparent why Schlumberger is interested in materials, but I'd let you explain it for us.
Okay, thanks very much, Tron, for the introduction, and very, very glad to be here today. It's an interesting audience. I've enjoyed talking with some of you. So Schlumberger was founded about 90 years ago. We provide drilling services, reservoir production services, reservoir characterization services to oil and gas production companies in about 80 countries around the world. Employ around 100,000 people, and each year we invest about $1 billion into research and engineering to improve our services. And today I'm going to give a few examples of how materials have allowed us to basically expand the boundaries of responsible hydrocarbon development. So this is a picture of reservoir development in an from about 100 years ago. And kind of the notable feature of that is the presence of these wooden drilling derricks everywhere someone wanted to create a well right down into the reservoir and produce the hydrocarbon. Today we still have reservoir developments happening around urban environments, and so the challenge the industry has embraced is to figure out what type of technologies can we apply to separate well the industrial activity from the urban activities. So a few of the examples I'll use are shown in this slide. Probably the most prominent has been the use of very, very long horizontal well bores that extend thousands of feet along the plane of the reservoir. And so these little red traces here, for example, illustrate such a thing. You drill down to a target reservoir and then out thousands of feet away. What this enables you to do is to cluster wellheads at one specific site and then access a large area of the reservoir from one particular site that may be very, very far from where the surface activity is. Once you have such a long horizontal wellbore, the next thing you want to be able to do is figure out how to subdivide that into manageable pieces so you can work on it effectively. And so I'll be talking a little bit about some simple wellbore staging tools that have enabled us to do that. And once you have this wellbore segmented, you can then connect it efficiently to the reservoir, and I'll be talking a little bit about a hydraulic fracturing process. So consider the wellbore that's depicted in this image. It comes from the surface to a reservoir target. Let's imagine that's a productive interval that may be 8,000 or 10,000 feet deep. And once the drill bit approaches that target, it then turns horizontal and it will track along that plane, as I said before, for maybe 5,000 or 10,000 feet. These are normal figures for the wells these days. And the amount of surface activity associated with that drilling process is directly related to how fast the bit can penetrate the earth, how many hours or meters per hour you can achieve. And the other thing is how much time you're actually spent drilling as opposed to removing the drill bits and the assemblies downhole to replace worn out and broken parts. And so the industry has spent an enormous amount of time and effort coming up with very specific and hard, durable cutting elements, figuring out how to bond them to substrates, how to then affix them into these drill bits, and indeed the body of that bit itself. There's very complicated metallurgy that's durable and can withstand all the forces. Another area of investment has been what we call the bottom hole assembly. This is an image of a rotary steerable system, which is kind of the most advanced type systems. And what it represents is there's a complicated mechanism inside that device as it's spinning that applies forces to the borehole walls to keep the drill bit pointed in the optimal trajectory, so you can take a very clean path as you're drilling. This device has wear pads that have to withstand being ground against the borehole walls. It has all sorts of internal bearing surfaces and seals, and we've had to come up with the materials again that can survive the torture that it's experiencing during the drilling process. And the culmination of all this has led to drill bits and bottom hole assemblies that are now reliable enough and durable enough to survive and allow us to drill these complicated long well bores in one run. And the impact of that is that now you can take a well that in the past might have taken 40 or so days to drill, and you reduce that drilling time by half, and that's a significant improvement. Once you have these long horizontal well bores, again, this might be 5,000 or 10,000 feet long, the next thing you do is you stabilize it by running in a steel casing, cementing it in place, and now you have to figure out how to connect that efficiently with the reservoir to produce hydrocarbons. And so, again, this is a matter of figuring out what type of tools and techniques we can use to subdivide that into smaller segments. On the left side here, I'm depicting a situation where we have a not very accurate method of controlling the placement of the hydraulic fracture. The fracture is what connects the reservoir to the well. And what the result is that you have kind of a non-uniform placement of these hydraulic fractures. You have large portions of the well that are essentially not connected, they're bypassed. That part of the reservoir is not going to be produced. It's an inefficiency. On the right-hand side, we're depicting a process that resulted in a much more precise placement of these hydraulic fractures to uniformly and effectively recover the hydrocarbons. And the question is, how do you achieve this type of decoration of the wellbore without adding too much operational complexity and cost? And so this is one example in this slide here of how we do that. So this is a device. It's a little staging tool. It's about this big, and it comprises of two parts. There's a collet that is deployed in the wellbore. It's affixed into the borehole, running on the end of what's called a perforating gun assembly. Once it's fixed there, the perforation tool is pulled up hole, creates holes in the casing so that we can pump through and create the hydraulic fracture. At the leading edge of the hydraulic fracturing treatment, we'll actually pump down the second component, which is a ball that seals against that collet. And this device has to withstand differential pressures of on the order of 10,000 psi, and it seals and protects the further extremes of that wellbore during the hydraulic fracture treatment. And so you repeat this process of deploying the collet and sealing and hydraulic fracturing 20 or 30 times to complete the well. And at the end of that process, ordinarily, you would need to mobilize a milling unit and come in and drill out all these plugs. And that's an operation that takes 1.5 or 2 days. It costs about $150,000. But the beauty of the system like this is it's fabricated entirely out of degradable materials. So these are these metal matrix composites. And it has properties that they achieve nearly the strength of steel, but when they're exposed to the hydrocarbon fluids, they disintegrate and leaving no trace within a matter of weeks. So you eliminate entirely that process of milling. And then the third example that I'm going to talk about is the hydraulic fracturing process itself. This is a depiction of what hydraulic fracture network may look like in blue, emanating from the wellbore in green. And so to give a sense of scale, the hydraulic fracture network may extend several hundred feet away from the wellbore. It might be tens of feet high, and the thickness or the width of those channels are a few tenths of an inch. They're quite narrow. And we create these by injecting water-like fluids or viscous fluids that might be cross-linked to create the geometry, and then we maintain those fractures open by conveying proppant, which is either sand or fine ceramic beads, into the crack. Now, the proppant is depicted in brown here, and the issue is there's an inefficiency in conveying high-density material in water. And so what we typically find is only about 40% of the created hydraulic surface area is propped open and remains productive. So there's a lot of opportunity to improve the efficiency there. Well, what we found is that by taking very fine fibers and dispersing them throughout the fluid, we're able to significantly improve the efficiency of the proppant transport, and that leads to improvements in well performance. And moreover is that once we come to the end of pumping, the fibers interact with the fracture wall, and they keep the proppant well suspended and anchored along the fracture face so they don't fall to the bottom where they don't have any effect. These materials need to degrade in the reservoir so they don't impair the flow field or the fluids that are flowing, and so we tailor the composition of these degradable fibers. The impact is that wells, the fracture networks produce about 25% more effectively, and we do that with about 40% less water, 40% less materials. So that concludes a few examples of how materials, a lot of them are enabled by nanotechnology and so forth. And I've listed a few other areas where we have additional, places where enabling material science can help us make similar type of advances, and we continue to be interested in these things. So hopefully through the rest of the morning I get an opportunity to talk with some of you people who have interest in these types of problems. Well,